Hi everyone, welcome to the AI Symposium. My name is David Churchill. I'm an associate professor in the computer science department here at MUN, and today I'm going to be talking about an introduction to artificial intelligence. First, I wanted to give a brief overview of what this presentation is going to be about. So first, we're going to talk about what is artificial intelligence, and then we'll show some examples of what artificial intelligence can actually do. We'll talk about some current state-of-the-art techniques for AI, and I'll end with a brief overview of my area of research and the AI lab that I've set up in the computer science department. So what is artificial intelligence? If you ask 10 different AI researchers what AI actually is, you'll probably get 10 different responses. But what I've done is I've just picked out 2 different definitions which I believe sum it up in a nice way. The first definition I found, and yes, this is straight from Wikipedia, is that artificial intelligence is intelligence demonstrated by machines, unlike the so-called natural intelligence demonstrated by humans and animals. But this is a bit of an abstract definition, so let's get a little bit more concrete with that. So AI as a research discipline involves constructing machines or writing software which makes decisions and/or takes actions in order to maximize its probability of achieving a specific goal in a given environment. But in my opinion, definitions like this, they're kind of boring, and they're going to vary greatly depending on who you're talking to and what field they're in. And so instead of just giving definitions, let's instead look at some application examples of what AI can actually do. First, let's look at the area of planning and scheduling. This is one of the oldest areas of artificial intelligence, and has been around since the 1950s and 1960s. In planning and scheduling, we try and develop algorithms and techniques for solving problems, such as here in Google Maps, where we're trying to find the shortest path, say, from the Avalon Mall to Signal Hill. So in the Google Maps application, behind the scenes, they're using planning and scheduling algorithms to determine these shortest paths. Next, we have the area of autonomous control, which is really popular, especially among people in robotics. Here I've given 2 examples of different self-driving cars, which apply autonomous control techniques in order to navigate by themselves without human control between one point and a destination. Self-driving cars have been around for more than a decade and have driven millions of kilometers all over North America and have demonstrated fewer accidents than human drivers, and are really one of the modern success stories of applying artificial intelligence to real-world problems. Next, we have image processing and pattern recognition. Over here on the left, I've demonstrated a very old problem, which is optical character recognition. So believe it or not, all of the mail that you've sent since the late 1980s and early 1990s has actually had addresses being scanned by computer algorithms. And these algorithms are already better than humans when it comes to problems like identifying written characters in text. Over here on the right-hand side of the slide, we can see an AI doing facial recognition. And it turns out that AI algorithms are also better than humans at identifying faces. Next up, we have the topic of AI in healthcare. And I think going forward for our society, this is going to be one of the most important topics that we pursue as AI researchers. One example of AI in healthcare that I've shown here on the left is the research area of AI-assisted surgeries. And we're already seeing this pop up more and more in actual operations. Another example application in healthcare, which we can see on the right, is identifying the location and size of brain tumors in MRI images. For years now, doctors and researchers have been collaborating on this technique, and it's already better than human doctors at identifying the location and sizes of brain tumors in these images. Next up, we have the area of robotics, and of course, robotics has been involved in artificial intelligence for decades now. On the left here, I show an example of the area of swarm robotics. In swarm robotics, you have many small or unintelligent robots which, when they come together, can accomplish really intelligent tasks. On the right-hand side, we see the opposite side of this spectrum, where we have a single intelligent robot that can accomplish many tasks on its own. Something that many people are unaware of is the creative side of artificial intelligence. So if you were a musician or an artist and you thought your job was safe from AI, well, you're going to have to think again. There are actually entire conferences devoted just to the topic of AI musical composition. And recent studies have shown that when AI-generated music is played for humans, they actually can't tell that it wasn't made by humans. Next up, we have the field of visual arts. On the left here, you see this nightmare fuel video which was created by the Google Deep Dream project, which is able to train a deep neural network on many images and then combine them in scary ways. On the right-hand side, I've given an example of a more modern field of research, which is called style transfer. With style transfer, you take an input image, for example, a video of this disco ball, and then you do deep learning on a bunch of paintings or images from a particular artist. And the output of this deep neural network actually can apply the style of that artist to the input video. And the results from this type of research are actually incredible. I encourage you to go online and look at some of these examples. Next up, we have the area of language processing and translation. So we already have some great success stories in this field with programs such as Google Translate. In fact, when I went to Japan a few years back, I was able to open up Google Translate, and as you can see in this image here, you can just take an image or a video of a piece of text in a foreign language, and it will translate it and put it into your video in real time. This is an incredible application, and if you haven't tried it out yet, I highly recommend trying it. Another important area of artificial intelligence is actually in the playing of games, and I'll get back to this a bit later in the talk because that's my area of research. So as we've seen now, artificial intelligence research can be applied to many different application domains. So if we try and categorize AI, we're talking about one of two different things. Either we're talking about the different types of algorithmic techniques that can be used for artificial intelligence, or we're going to talk about the application domains of artificial intelligence. So for example, if you talk to someone in computer science, it's probable that they're working on more of the fundamental algorithmic techniques for AI. Whereas someone outside of the sciences may just be using artificial intelligence as a tool to solve one of the problems in their application domain. On this slide, we can see just some of the more popular categories for AI research. For example, machine learning, natural language processing, speech processing, expert systems, planning, scheduling, and optimization, robotics, and computer vision. And in case you were curious, my particular fields of research are in the areas of planning, scheduling, and optimization, robotics, and machine learning. Now let's talk about some of the current state-of-the-art techniques for solving modern artificial intelligence problems. Most of the techniques implemented in the past few years have centered around two main types of systems, those based on machine learning and those based on heuristic search. Machine learning techniques can be separated into three main categories. First, we have supervised learning, in which machine learning models are trained to predict values based on correctly labeled training data. For example, if trained on labeled images of cats and dogs, say, a supervised learning model could then predict whether a new unseen image looks more like a cat or a dog. Unsupervised learning, which is given no labeled data, instead attempts to find underlying patterns in the data. For example, we could have data clustering. So given some input data, we could group them into clusters of similar features so that you can do more analysis on them later. And lastly, we have reinforcement learning, in which agents explore their environment and learn which actions are best by analyzing the rewards they get from performing them. The great thing about reinforcement learning is that it operates much like the way humans learn. For example, if a child is exploring its environment and touches a hot stove, it's given a negative reward in the form of pain, and will most likely not do that again in the future. Unlike machine learning, search-based AI systems are not trained in advance, but instead they operate in real time. Search algorithms exhaustively explore all possible actions within an environment, and then examine their outcomes in order to determine which sequence of action best leads the agent towards its goal. One upside of search algorithms is that they do not require an offline training phase, or large amounts of data to be collected. However, they do require a working model of their environment, and so sometimes they cannot be applied to real-world applications. So in the past, researchers would often focus on using either search or machine learning in order to solve a problem within a given domain. But more recently, in the past 5 or 6 years, researchers have been combining the exploration of heuristic search algorithms with the learning of policies and state evaluations of machine learning in order to produce better results than either one of them could have produced on their own. One recent really famous success of an AI system that combined search and learning was Google DeepMind's AlphaGo program, which defeated the human world champion at the board game of Go in 2016. After the Deep Blue AI system defeated the world champion Garry Kasparov in 1997 at the game of chess, Go was really the last remaining popular board game in which humans still dominated AI agents. In the early 2010s, a lot of professional Go players, as well as AI researchers, thought that it might be decades before AI systems were able to beat the world champion at the game. However, by combining Monte Carlo tree search, a form of heuristic search, with deep learning, along with using massive parallel computation, AlphaGo was able to beat the world champion Lee Sedol 4-1 in a tournament match. Here we can see an overview of the architecture of AlphaZero, which was DeepMind's successor to AlphaGo. AlphaZero used a combination of heuristic search, which you can see up top here, and deep reinforcement learning, which you can see down here, to reach skill levels far beyond the original version of AlphaGo and way beyond the skill level of any human player. So now we can see that modern AI systems are capable of outperforming the decision-making power of some of the world's most intelligent humans in their given domains. And as AI power approaches this level, we can actually start to imagine the type of real-world benefit that this may have for us as an everyday society. One quote that I saw on this topic that I really liked was that the Industrial Revolution created machines to do our heavy lifting. The AI revolution will create machines to do our heavy thinking. And as such, everyone can use AI. One example of the real-world benefit of AI here in Newfoundland specifically is Verafin. Verafin's a local software company that specializes in developing banking software to help detect criminal activity such as financial fraud and money laundering. By using machine learning, they can analyze the transaction records associated with past cases of fraud and learn to predict when future cases of fraud may occur. Another example of a local company is Virtual Marine. They specialize in creating training simulations for all types of real-world scenarios, such as marine navigation, search and rescue, etc. By incorporating modern AI systems into their simulators, they're able to make the simulators more realistic and deliver better training to their customers. And with this better training, it may end up actually saving lives in the future. The last example that I'll mention came up in a discussion with Environment Canada and the forestry industry. By employing techniques such as scheduling and planning algorithms to the thousands and thousands of trucks and other heavy machinery that they use in the forestry industry, it could potentially save not only millions of dollars in fuel costs, but it also could cut down dramatically on the environmental impact of things such as pollution caused by the transporting of goods in the forestry industry. Another really important benefit of doing AI research is in HQP development. For example, AI programmers are in extremely high demand these days. AI companies are hiring in large numbers. There are actually many positions currently available in St. John's for AI developers. And data science jobs are paying great salaries and are very closely related to AI training. And also, AI motivates students to learn. AI is a super fun topic to teach. Students enjoy learning, and I've found in my courses that deal with AI, and especially AI in games, there's a lot more class engagement in those courses than courses that don't involve AI in games. So how do we actually do AI research and development? What does the process look like that we have to take in order to come up with a new AI system? Well, first, we have to identify a problem or an area to work in. So say, for example, you may really care about neural networks. And so you say, I'm going to do some research in how to improve the performance of neural networks. Or you may have a problem domain that you really care about. For example, the forestry industry. And so you'll take an algorithm and try and apply it to that specific industry. Next, what you'll do after you've identified a problem is you'll do a literature review of the existing techniques to solve that problem. Because of course, as researchers, we don't want to reinvent the wheel. Then we'll develop new techniques. So, in general, this is really difficult. So this is kind of where the magic occurs. And then we'll test those new techniques against existing state-of-the-art algorithms under specific controlled circumstances. And then if your new technique is better than the previous state-of-the-art technique, then you can publish. One important step in that pipeline was the testing of the AI systems. But how do we actually do that testing? Well, if you think about it, how will we determine whether or not one system is more intelligent than another system? That's actually a difficult problem. So one thing that AI researchers have been doing in recent years is playing games with their AI system. And the reason is that for the most part, games measure intelligence. Now, when I talk about games, I also mean simulations, right? So we could have a training simulator, for example, Virtual Marine. I would consider that a game as well. So some of the benefits of doing AI research and testing with games and simulations is that games can simulate the real world. Therefore, if they can simulate the real world, then any AI solution that performs well in the game should also translate well to real-world problems. Something that's very convenient for researchers as well is that there's no ethics required for games. So, you can train an agent to do something in a video game that might not be allowed to do in the real world. Games and simulations are fairly cheap compared to real-world testing. You can go buy a video game and do testing in that for as little as $100. Games are extremely easy to visualize, and they're intuitive to analyze as well. So if you come up with a system that uses AI, for example, to play the game of chess, you can really easily go out and find a bunch of experts at chess to analyze your program to see where it's making mistakes or where improvements could be made. Also, games and simulations are just super fun to program and play and work with, and so it's way easier to find good people to work on these problems if they're fun to program and play. And also something that I really care about is that games and simulations really help motivate people, and they help students to learn because they're more fun than traditional educational systems. So over the past few decades, in AI research, we've sort of seen this trend of human versus machine appearing, in which we want to beat the world's best humans in particular domains. And of course, we've traditionally used games for that. So for example, as I said before, there are world champion AI systems that are able to beat humans at the game of chess. The game of checkers was actually solved, meaning that every position in the game of checkers has actually been enumerated. That was done by Jonathan Schaefer at the University of Alberta. In 2016, the board game of Go was dominated by AI. And so now what we're doing is we're actually transitioning away from traditional board games into more video games. And there are still several video games, such as StarCraft, League of Legends, Dota 2, that are so complex and so hard to play that AI systems still have not conquered humans in those. And so over the past few years, AI researchers are transitioning away from traditional board games to more modern video games due to their complexity. So why are AI researchers turning to things like video games in order to test their algorithms? Well, it turns out that many video games have really difficult properties. For example, video games are played in real time. They're not alternating move games like chess, where you may have several seconds or even minutes to take your turn. In video games, if you're not acting right now, then your opponent could get you before you have a chance. And so the real-time nature of video games makes them much more complex than traditional games. Also, video games have simultaneous moves, which introduce really interesting complexity properties. Video games can be non-deterministic, meaning that there's some randomness in the game that now your AI has to deal with. Also, they can be imperfect information, meaning that some players have access to some parts of the game, and some players have access to other parts of the game. And if you don't know things like, for example, where your opponent's units are or what cards they're holding in their hand, then that can be a really difficult problem to solve. Also, we have issues like multi-unit control. So unlike a board game where you're, say, moving one chess piece between different spots on a board, now you may be moving multiple units, up to dozens or hundreds of units. And that sort of combinatorial explosion makes these games really difficult to play. Also, we may not know the physics of our game engines. And so, unlike board games, whose rules have been known for hundreds of years and they're very easy to program, we may be trying to do AI for systems that we don't know the game engine for. Also, the action and state spaces of video games are much higher than traditional board games. And the action and state space meaning how many possible actions can we take at a time, or how many possible configurations of the environment are there. And if we look at this, the properties of video games are actually the same problems that we face in robotics. And not only robotics, but these are also the properties of the real world. And so the idea here is that if we can come up with AI systems that perform well in complex video games, then we can translate those solutions into real-world problems. And really quickly, with the minute or two that I have left, I wanted to talk a bit about the MUN AI and Games Lab in the Computer Science Department. So the lab is currently funded by ongoing grants from NSERC, ACOA, Innovate NL, with some additional funding from Facebook AI Research and Google DeepMind. Here's a photo of some of the students in the lab back when they were actually allowed to visit the lab. And very briefly, I'd like to list some of our current research projects that are going on inside the lab. First, we have the International StarCraft AI Competition. It's organized and run out of the AI and Games Lab by myself and one of my master's students, Richard Kelly. In this competition, people from all over the world submit their state-of-the-art StarCraft AI bots to compete in our tournament. The competition has been going for over 10 years, and over the years we've gotten submissions from many countries, and it continues to be one of the premier AI competitions in the world. On that note, we also have a couple of ongoing research projects related to real-time strategy games, StarCraft in particular. One of these projects involves using deep reinforcement learning for in-game unit micromanagement, and has so far been successful in improving the state-of-the-art in a field called transfer learning. We also do research in reinforcement learning for autonomous robotics. For example, one project of a recently graduated master's student was in the topic of reinforcement learning for pattern formation. In this video, we can see that the small blue robot is using reinforcement learning to construct donut-shaped patterns from the red-colored pucks on the floor by pushing them around the environment. We also do projects on AI for video game development and design. For example, we do research in the area of procedural content generation, or PCG, for video games. In PCG, we use AI techniques to automatically generate content, such as new levels for video games. In this slide, we can see one of these algorithms in action, which is capable of generating a near infinite number of dungeon maps for gamers to enjoy. And finally, I'd just like to briefly point out the different computer science courses that we have relating to video games and AI, in case you're interested in taking any of them. So in computer science, we have a number of these courses. For example, Computer Science 3200, which is the Intro to AI course that I teach. There's also Computer Science 3201, which is Nature-Inspired Computing. 3202, which is Intro to Machine Learning. Then there's 4300, which is Introduction to Game Programming. And finally, 4303, which is AI in Computer Games. So that's all I have for today. Thank you so much for listening, and I'm open for any questions.